Thank you all so much for coming here. I know it's the end of the day, and some of us have had a long day at the TRI annual review, so thank you again for being here. I can tell you that I looked for the big giant check somewhere in this room. I couldn't find it. So if you were here for, see me holding something up? Okay, so thank you so much to Toyota for endowing this professorship at the university, and of course, thank you very much to the leadership of the college to select me for this great honor. Thank you, Alec. Thank you, Michael. Thank you, others in the leadership. So before I begin into the professional part of this talk, I want to thank the three people near and dear to my heart. The fourth one will come in later. My wife for 25 plus years, Ruhi, my two daughters, Hanel and Maya, who are sitting in the audience. Thank you again for all the love and support for all these years. Now, as you can imagine, somebody who's worked for so long in the field, I have literally stood on the shoulders of students. So that's me at the top. There's Eric, and that's Nan. And of course, just like I stand on the shoulders of students, I had great mentors standing on me. I've been extremely fortunate to have two amazing people who have been very strong mentors for me. My PhD advisor, Andy Bartow, who started this field of modern reinforcement learning in his lab back at UMass Amherst. I was about the 7th or 8th student in his group. So one advice to grad students in the audience, be the 7th or 8th student or something like that in a field. Pick a new field. The other person I want to acknowledge is Mike Jordan, who I did a postdoc with at MIT. He's now at Berkeley, and he literally is the Michael Jordan of the field of machine learning. So I have had really amazing, amazing mentors. And of course, here's just a quick view of all my former students and postdocs whom I've collaborated, some of whose photographs I couldn't find. And here are my heartfelt thanks to many of my CSE faculty collaborators as well. Okay, so now, as is customary in this talk, by the way, if anybody who's here for theorems, now is the time to leave. This is going to be a very general talk. So here's my view, my very subjective view of the field of AI. By the way, I joined in 1987 my PhD, and my PhD lasted from 1987 to 1993. Today I looked up the AI winter period, and apparently it turns out AI winter 2 was exactly in 1987 to 1993. So that's when I was doing my PhD. So my PhD was the bottoming of this hill of AI interest, or at least self-proclaimed interest in AI. So before that time, the biggest thing in AI was expert systems. And that's when everybody was proud of doing AI. And then suddenly, AI became a bad word, and it was learning. Everybody was doing learning. And now interest in AI is climbing back up as we become interested in autonomy. So back in the day of expert systems, the emphasis was on knowledge engineering. So people work hard to try to define knowledge into systematic programs and then do inference and planning with those hard effort into knowledge engineering. Then came the learning phase, where statistics and supervised learning took over. And everybody became a machine learning researcher rather than an AI researcher. The word AI was mentioned in hushed tones and friends. And then the phase we're just starting, which is the climb up to autonomy, in my view, which is the phase in which deep learning and unsupervised learning and reinforcement learning has become very popular. I've suddenly gone from a field where, in the reinforcement learning conference sessions at the machine learning conferences, there would be 20 people to now 2,000 people. It's that dramatic a shift in the last just few years. And it's been fantastic to be a beneficiary of that great sudden surge of interest. So that's the view, sort of this valley that we're climbing out of from learning to autonomy that I'm going to spend some time with. So lest you think that, by the way, expert systems are a thing of the past, here is a set of charts that I found from one of the people who are paid to prognosticate, in which these different bars correspond to different AI technologies. So the first set of bars are for expert systems. The second for autonomous robots. You probably can't see. The third one is digital assistants. The height of the gray bars is the total market size for AI. And you can see that 2024 is a large market, and the market's increasing in AI. And the blue curves in each of these set of bar charts are for the different technologies. So expert systems remains a huge deal in industry even today. So all of these ideas that have come through, of course, continue to play an important role in industry as well as in academia. Okay, so now I want to take a few minutes to place reinforcement learning in the broader context of learning itself, of machine learning itself. Okay, so I apologize for the 80% of you who know what supervised learning is, but I'm going to spend a little time just describing what supervised learning is. So as far as I know, what supervised learning is a problem of finding cats on the web. That's what supervised learning is. And here is the most prototypical example of such things. You find cats in pictures on the web. Such is the obsession with cats in supervised learning that now we have fake cats generated by neural networks. So here are fake cats generated by a neural network that has learned to generate cat images, and has been trained by cat images. Talking about cats, here's the fourth member of our family whom I must pay homage to. My cat, Luna. I have to be sure to be able to get home tonight and be led inside her house. So thank you, Luna. So how does supervised learning work? Well, you take images and you pay somebody or you figure out a way to label them. So here are images on the left of cats, on the right of dogs. You give a system these images that are labeled as cats and dogs. This is a set of data from the Kaggle data set. And then you build what's called a classifier. So here's an example. Somehow animals is a theme today. This is a distinction between sheep and goats. The x-axis is the number of steps the animal takes per day. The y-axis is the mean daily temperature in degrees. Each dot or triangle in this two-dimensional plot is an example, say, of measurements from an animal, either a sheep or a goat. And the line that separates the blue from the yellow pieces is the separator between goats and sheep. So there are lots and lots of different ways of doing supervised learning, decision trees, SVMs, your favorite classifier. And the bottom line, if supervised learning has a bottom line, it is this. If it is possible to collect data, collect well-labeled data, cheaply in a domain, supervised learning will likely solve this problem. Now, this seems like a simple statement, but it has enormous consequences for society because lots and lots of things do fall into this category where we can collect well-labeled data reasonably efficiently. And my colleagues in the data on the crowdsourcing side are innovating in ways of doing this for more and more problems, and which means that lots and lots of jobs in which this kind of expertise is needed is, of course, under threat using this kind of machine learning and supervised learning. So that's the bottom line of supervised learning. We really, if you give us a well-defined problem and a data set, we can build a machine that can do that problem. Okay, so what's reinforcement learning and how is it different from supervised learning? So I like to say, as Mike anticipated, reinforcement learning is the full problem of life. You have an agent, shown as a robot in this blue agent-looking thing, interacting with some environment. It has some sensors through which it perceives the environment. It takes actions in the environment and occasionally receives a reward. This is how life works, right? We have sensors, we have eyes, we have touch sensors, we have ears, and so on. We have sensors, we interact with the world, we take actions in the world, and we change the world as we act in it. Of course, other creatures in the world also change the world, but this is the closed-loop dynamics of a reinforcement learning problem. It's a sequential decision-making problem. It's quite different from the supervised learning problem. Okay, so I'm going to show you just a couple of examples of reinforcement learning. So here is a now well-studied problem in reinforcement learning, Atari games. There's a company called DeepMind that actually built this first game-playing systems using reinforcement learning that were able to outperform humans and did fabulously well by just that kind of demonstration. So I want you to understand the difficulty of this problem from a reinforcement learning point of view. So when you actually play Atari games, you have a joystick. You're choosing actions for the joystick. So the system is getting exactly this image that you're seeing. Now, when we see this image, we recognize there's a paddle, there's a ball, there are blocks. The objective is to break the blocks, but the system knows none of that. It's just getting this camera image. It has this discrete choice of actions. Maybe there are 18 actions of moving the paddle in this instance. and it gets a score. The score is on top. And it has to learn through trial and error how to achieve high score. That's a remarkably difficult problem because it knows nothing about what's going on in this image. What's happening is just seeing these pixel array images. And it's trying to discover through trial and error, through acting in the world, what policy, what strategy, what choice of actions leads to a high score. And life is a bit like that. We have to do things in the world. We have to try things and learn from what happens when we try things. The other very famous image is Alphago, which hopefully all of you have heard of or seen, which is a very recent success, again from DeepMind, which used reinforcement learning to build the best Go-playing system, such a good system that actually beats the best human player in a match that was widely televised. Again, a very similar problem. You have a Go board. When we see a Go board, we understand so much, but of course, that's just getting a raw pixel image, if you like, of the Go board and has to decide, and it knows what actions are legal and has to learn through trial and error of how to play Go, and it learns to play Go so well that it actually beats the best Go player. So that's the reinforcement learning problem, how to learn to act through trial and error by interacting with an environment. Okay, so is reinforcement learning in the same advanced state as supervised learning? The answer is yes and no. And I'll elaborate on both of these as we go along. Okay, so now I want to get a little tiny bit technical and tell you a little bit more about how we go from supervised learning to reinforcement learning to the bigger question that I call continual learning, that to me is a big push towards AI. So the main technical challenge in supervised learning is called generalization. I train on 1,000 cat images, then I'm given new images, and I have to take unseen images and label them as with cats or not having cats. The main technical challenge in reinforcement learning are twofold on top of the generalization challenge. The first one is called the explore-exploit problem, or exploration-exploitation, and the other one is called delayed reward. Let's think about exploration-exploitation for a minute. I'm playing Atari games. I'm trying to learn how to play an Atari game. I figure out a way that I can get a little bit of score. Now, at that point, I've learned a little bit. Should I choose to exploit? That is to do what I know will give me a little bit of score. Or should I try some things that I haven't tried so much or that haven't looked so good? That is to explore, because maybe then I will discover something that will lead down the road to even bigger rewards, higher scores. So that's the fundamental hard problem in reinforcement learning. It's called the exploration-exploitation problem. And we face it every day as we act in the world. The other problem is the delayed reward problem. What's the delayed reward problem? Well, let's say I imagine I play a game of Go, and I win, or I lose. Let's say I lose. So now I've made 1,000 moves. Which move was responsible for that loss? It could have been that the 18th move is the wrong move, and everything else was perfect. And the wrong move at the 18th step led to this delayed consequence after 1,000 steps of a bad outcome. And that's the delayed reward problem. How do you figure out what was responsible for this delayed consequence? Again, this is a hallmark of life. We do things. All of you who are grad students are facing this problem. You're delaying your reward, right? You could be earning a lot of money right now if you just worked for a company. But instead, you're delaying, you're taking actions now with the hope of a bigger delayed reward. So that's the problems that reinforcement learning brings. I think to get to AI, we have to go one step further. And you can call it whatever, but my company calls it continual learning, which has the extra fourth problem, which is the difference between supervised learning and reinforcement learning is supervised learning, you learn from a teacher-generated data, right? Somebody labels cats. In reinforcement learning, we learn from self-generated data, but teacher-provided task. So the teacher provides a reward function, and we learn how to optimize the reward from trial and error. Life is not like that. It has to be autonomous learning, has to be self-motivated. So the additional question on top of reinforcement learning is what to learn, is what to do with our time so that we can, the experience we get and the computational resources and the representational resources that we have available to us. What do we do with that? What do we learn? And that's the problem of intrinsic drives, intrinsic motivations. And I think to get to AI, we have to go all the way past reinforcement learning into this continual learning space. Okay, so I know that many of you would be disappointed if I don't at least tell you something technical. So let me try a little bit about exploration exploitation. So this is the problem a grad student faces as they walk down a corridor of offices. Which office will have leftover pizza? Right? Many of you, other than Jesse and I, all of you are young enough to have been grad students recently enough that you can imagine these days. So you're always looking for free food. You open a door, there might be food behind it, there might not be. So opening a door is like choosing an action. Finding a pizza behind it or not finding it is a reward, or not finding a reward. And so every day, you have to decide which doors to open. This is the exploration exploitation problem. Because maybe, the first 3 days, there was pizza behind the first left door. That doesn't mean it's going to be there on the 4th day. It might be the next room over. So this is the exploration exploitation problem. And I, with a colleague at AT&T Labs, Michael Kearns, came up with an idea that we termed the optimism in the face of uncertainty. It's a fundamental idea for solving this problem. So optimism in the face of uncertainty is the idea that says, look, if I haven't tried something, there's a good chance that behind it, there is a lot of reward. So if I'm uncertain about the outcome of a certain action, I want to be optimistic about it. Because then I will automatically explore that choice of action when I have that opportunity. Because I'm going to be optimistic about that thing that I don't know enough about. And this can be mathematized. And you can do things like upper confidence intervals, upper confidence bounds, and how much confidence you have about your estimate of the reward for each choice of action. And then use that in order to guarantee that you will do well in the long run in this exploration exploitation problem. So this was already known in a sense for what is the simple version of this problem, which is called the Bandit Problem. The Bandit Problem is the problem which is described to you. Every day the student walks down and has to decide which door to open in the hope of finding pizza. A much more interesting problem is a problem like Go, where there's state, where as you try things, the state changes, and if you learn what to do in each different state. So it's a Markov decision process, and that's what we provided a key new result all these years back. So this is the form of the result. We showed that using this idea of optimism under uncertainty, an agent can guarantee in a general Markov decision process, the kind of thing that Go is, cumulative reward that is near optimal in time polynomial, which as computer scientists we care a lot about, in the number of states and actions, and what was a new idea then, mixing time. I'll break it down a little bit in a minute. So the reason why this result got a lot of attention is the previously known result was that learning in general Markov decision processes is in fact not polynomial. And here we were saying it's polynomial. And the difference was that it's polynomial in the mixing time. So what's the mixing time? Roughly speaking, the mixing time of this kind of sequential process is the time it'll take you to get to any state you want to get to. It's not quite accurate, but it's approximation. If that time, if the world is such that it can take you a very long time to mix, to find the stationary distribution, to get to a state that you want to get to, then, of course, no way of behaving can be efficient. So you can't learn efficiently. And so what we ended up showing, and I apologize for being very quick about it, is that the only way that learning is not polynomial is if the mixing time of the dynamics of the world is not polynomial. This was a very interesting result. It led to a whole slew of follow-up results that have followed up and solved the exploration exploitation problem. I'm going to give you a little bit of how to do optimism under uncertainty in this general Markov decision processes. So I'm showing you a visual representation of a Markov decision process. Each node is a state. Think of a state as a Go board, for example, or a frame of an Atari game. The choice of actions are denoted in color, so there are two choices of actions, red actions and green actions. And they transition the world among states. And these are probabilistic actions, so the probability of each action is noted on the edge. So for example, the green action takes 0.9 with 0.9 probability will take you to state 1, and 0.1 probability will take you to state 5. So the bottom line idea for optimism under uncertainty is any given point of time, the agent will know some states really well because it has experienced them a lot, and some other states not so well because it has not experienced them so much. All the states that it knows about are shown in solid. All the states that it has uncertainty about are shown in dashed circles. So the idea of optimism under uncertainty, which we exploited in this setting, was to say, look, everything we have uncertain about, we're going to imagine in one of two ways. In one way, we're going to imagine that it's absolutely the best place to be, extremely high reward, and then compute a policy, which will try to take us out of the known states into the unknown states. Separately, we'll assume that it is really, really bad, which will try to keep us in the known states. And it's the difference between the utility of those two that then yields an algorithm that provides us, so being optimistic that every uncertain state is a really desirable state leads to efficient exploration because it finds a good way to get to an unknown state from a known state. And that's what you need in order to gain more experience in the unknown states and convert them into known states. I'm doing this very fast, but this is the rough idea of optimism under uncertainty that leads to this very general result that has been fortunately influential in the field. Okay. Now there are several problems with this optimism under uncertainty view. One of it is shown in this diagram. There is such a thing as being too optimistic. So if you imagine every single door has behind it the best food you can ever imagine. By the way, this is known as the grad student syndrome, which is shiny objects everywhere. You never get satisfied with what you have. You're always finding a new shiny object somewhere, looking for a new shiny object. So this is that problem, where you're never satisfied with what you have. You never choose to exploit. You're always exploring. So this is the optimism under uncertainty gone amok. There's also another problem with optimism under uncertainty, which is, fine, there's cookies behind some door, maybe there is food behind some door, but there could also be a tiger behind a door, and you don't want to open that door. So how do you deal with optimism under uncertainty in safety-critical situations, where the wrong action can really get you eaten, and that would not be good. This is a problem I'll come back to at the very end. This is an open problem, by the way. We don't really have a great answer to how to do exploration and exploitation in safety-critical domains. Okay, I want to dive into delayed reward just briefly. Remember, delayed reward is the setting in which you act in the world, you don't get immediate feedback. After a long time, you get some feedback, and then you have to figure out what you did was good and what you did was bad back in time. So this is the delayed reward problem. So I'm going to tell you of a result that Nan and I did that I think just shows how a simple idea can lead to a really nice kind of result. So here's the idea. We're going to look at the setting where we gather experience in the world, and from that experience we build a model. By a model I mean we build something, a computational program that can predict future states given current state and action. So it can tell you what might happen. You can learn to simulate the world by building a computational model from data. So the planning method we're going to look at is we're going to gather data. We're going to take that data to build a model and then plan with that model. By plan, I mean look ahead, simulate what might happen, and then look for good things to do from that simulation. So that's planning with a learned model. Okay, so the problem with planning is in worlds in which there are many possible choices and there are many possible outcomes to the choices, is that planning really deeply is computationally expensive. It's exponential in the horizon, how deeply you plan. So most methods, they decrease planning horizon because they can't plan very deeply, because they want to save computational costs, but they acknowledge or understand that this leads to loss in performance. So you're trading off computational cost and planning loss in this way of selecting how deeply you plan. So that's the traditional view of planning. But I'm interested in the case where the model itself is learned from data. And the question is, how do you view this trade-off when you have a model that's not accurate, it's not the real world, and you have a model that's learned from data? And what we showed was quite a remarkable result, and I'll make the connection in supervised learning in a few minutes, is that we showed that the smaller the amount of data you have that went into building your model, the smaller the planning horizon you should use. Because, in a nutshell, the less data you have, the more noisy your model would be, and the deeper you plan, the more you'll be overfitting to the noise in that model. So the less experience you have, the shallower you should plan, because deeper planning is just going to fit to the noise in the model. Right? It's an intuitive, very, very simple, obvious looking thought, or obvious seeming thought, and we showed it, Nan showed it in a very nice theoretical way that I'll just briefly tell you about. So we showed this by analogy to a really fundamental, probably the fundamental result in supervised learning, which goes like this. When I teach 545, machine learning, I say if you get nothing else from this course but just what's on this slide, that's the key thing in supervised learning, which is the following. When we do supervised learning, we pick a hypothesis class. We have a class of models we are using data to select a model from. The larger the class of models, the smaller the error will be on the set we train on, because we can learn more from the training set. We can fit to the training set more, because we have a larger space of models, so we can find one that does well on the set we are training on. But as you increase the size of hypothesis class for a fixed data set size, test set error decreases beyond a point, because you overfit to the noise in the data. And so what you want to do is pick the size of hypothesis class that is commensurate with the amount of data you have. And this is a bread and butter statistical machine learning result in supervised learning. And furthermore, the more data you have, the larger the class of hypotheses, the larger the model class you can afford. So what Nan showed is that a longer planning horizon amounts to a larger hypothesis class you're searching over, so that we can replace the hypothesis class size by the planning horizon, how deeply you're planning. And he showed it formally in a beautiful result, very simple in some ways, to show that if your horizon is 1, if you're only going to act greedily, then essentially your space of policies you're searching over is size 1. Approximately, that's an approximate statement. That if you plan sufficiently large horizon, then essentially all policies are possible. What does that mean? It means that if I plan deeply enough, I can find worlds in which, with that kind of deep planning, any policy I want to make optimal can be made optimal. That is, all those hypotheses are possible. And furthermore showed that as you increase horizon, monotonically you go from a small horizon, small space of policies, hypothesis class, to a exponentially large space of hypotheses or a planning horizon class. Okay? And that led to this really nice result that as the planning horizon increases from 1 to infinity, the number of behaviors that become possible to be optimal grows monotonically from a small set to a very large set, which is now the analogy to supervised, to this bread and butter result in supervised learning that I just talked about. So the bottom line summary of this is the less experience you have, the less deeply you should plan, which makes sense. But it's a really nice way of showing all this. Now, I just wanted to show a video. But I'm going to make some points from this. This is another planning problem. It's a very simple planning problem. Every episode you get a new grid, or every episode you get a new grid. The agent, this is Minecraft. What the agent sees is this kind of visual first-person view. What we are seeing, just so we can see it, you're seeing a top-down view of the agent in the environment. So this is what's called partially observable problem, because all you're seeing is this local view from where you're looking. You don't get to see the global map. And the task in this grid, for example, is to, from this first-person view, learn a policy that finds first the red square and then the blue square. So it's looking for the blue, and then it finds red, and then it finds blue. And we'll make the task harder and harder. And all I'm showing you is that this seems like a really complicated problem from just this first-person view. What you're seeing on this side, you can learn using reinforcement learning how to solve this delayed reward problem, where only when you get to solve the task fully do you get a reward, and you're still able to learn really efficient strategies for solving mazes like this. Lest you think that, or at least lest my family thinks I only play games, I'm going to show you a couple of other problems where we use reinforcement learning. This is TRI-funded work, where we're using a robot in which the task is to pick up a block and move, or actually the block is where it's at. Somebody else is moving the green target region where you want to pick up the red block and take it. And you can see that it's learning from scratch. It's learning from no prior knowledge. It has 7 degrees of continuous degrees of freedom. It has joint angles as state space, and it's learning using reinforcement learning how to pick up a block or move a block into this target region. There on the right side, we showed how in a simulator that TRI has developed called Carla, and this is very, very preliminary work, the one on the right. In the first few episodes, the car does really badly. It has to turn around the corner and come to a stop. And then after a couple of thousand episodes of learning, you will see it's still not perfect, but it's going to be able to do it. One challenge that I want to highlight that I'm going to try to address is one of the challenges in solving this Carla problem is defining a reward function. Because one reward function you could say is, look, I want to get it to the stop sign, get to the stop sign as fast as possible. But that's not enough because it'll run over pedestrians, it'll do whatever it wants to do. So then you might say, well, it shouldn't run over the intersection, it shouldn't go on the pavement. But how much reward should you give, or how much penalty, if you like, should you give those kinds of states? And so designing a good reward function becomes a fundamental challenge in these kinds of robotics-like problems, which is the next part that I'm about to address. Okay, so that's this part. Where do rewards come from? The point of this slide, in part, is to say the reward really lies inside our heads, right? You might think a cookie is a reward. And of course, when we give somebody a cookie, we are intending to reward them. But it's just another sensation. It's just another experience. Whether we feel rewarded or not depends on our internal state. And it's our dopamine system, which is a part of our brain, a neurotransmitter in our brain, that actually is responsible for whether we feel it rewarding or not feel it rewarding. So unlike the reinforcement learning problem where the agent is given a reward by a teacher, if you like, by the reward designer, in the AI problem, rewards are internal. And so they could be fixed, but evolution presumably has done a really great job of designing our reward function. Let me just pause for a minute on evolution because I think this is a helpful way of thinking about the reward design problem that I'm about to get into. So what's our reward function? What's our reward function? I'm going to claim, and some of my AI colleagues might argue otherwise, but we're reinforcement learning agents, by and large. And that means we're reacting to reward signals. So what's our reward function? Now, evolution, of course, cares about species. And so if the reward function is only the act of procreating or passing on our genes, then with that as a reward function, it'll be extremely difficult because to do learning moment to moment. Because how much coffee should I drink today can't be determined by that. Maybe it ought to be. But so that reward function, the evolutionary fitness function, is extremely distal, right? It's extremely late in time and very sparse, extremely occasional. So that cannot be the reward function in our brains. So what's the reward function in our brains? So you can imagine as evolution, in a manner of speaking, reaches inside our brain and sort of tweaks it. It's tweaking our reward function also. So in principle, it could tweak the reward function all the way down to prescribing what we should do at every moment. But that would make us extremely inflexible as agents. Because basically then would have written down the exact program we should follow. So what evolution had, my hypothesis, my conjecture, should do, has done, is that it has found the right level of abstraction of rewards that are task independent, that are environment independent, so that no matter what environment we find ourselves in, we have reasonably proximal, close in time, and reasonably dense reward function. And that's the challenge, I think, for us to solve as AI people, is to figure out what those proximal and dense reward functions that would lead to really good behavior across the range of environments we want to put artificial agents in, or in the case of evolution, natural agents. Okay, so this is the idea of the reward belonging inside the agent rather than outside. So psychologists have thought about it. And they've come up with a list of these possible intrinsic drives or motivations. Novelty. We find novelty rewarding. Optimism under uncertainty. Improving our model, improving our predictions feels rewarding. Learning feels rewarding, which is like improving our prediction. Bayesian surprise, something we didn't expect from a Bayesian point of view. Information gain, all kinds of different computational mechanisms that are task independent, that could work across the range of possible environments we find ourselves in. If you're curious, we'll learn no matter what domain we are in. Right? That's a good reward function that can be proximal and much more dense than the distal evolutionary kind of reward function. Okay, so we took this idea and formulated a precise problem, which we call the optimal reward problem, which is a problem of, as AI people, we can think of it this way. I am the agent designer. I have an objective reward R sub O. I want to design a reward function that's internal to the agent. So in the evolutionary story, evolution is the agent designer. The agent is natural agents in the evolutionary story. And the bottom line of this sort of slightly mathy slide is the optimal reward is the reward one would design for an agent so that no matter what environment it's in or the distribution of environments in expectation, it would optimize the agent designer's reward. So this makes a concrete optimal optimization problem, and we can begin to solve it. By the way, how am I doing for time? Where's Teresa? She's grimacing. So let me skip all of this and just go down to this. So we've done a lot of work on optimal rewards. Okay. I want to just say this because, of course, you can never go wrong by quoting Vannevar Bush. So I'm just going to do it because, of course, we are in a university. The scientist doing basic research may not be at all interested in the practical applications of his work. Yet the further progress of industrial development would eventually stagnate if basic scientific research were long neglected. Basic research leads to new knowledge. Curiosity, intrinsic motivation leads to new knowledge. It provides the scientific capital. It creates the fund of scientific capital from which the practical applications of knowledge must be drawn. Really hits home the idea of intrinsic drives, intrinsic motivation, because that's what we do every day. We seek knowledge without necessarily looking for practical applications. Okay, I'm out of time. I'll just do a quick big picture thing and then we'll be done. Here's the personal dilemma I face when I do my research that I want to share with you. And of course, some of my colleagues will have different views on this. We want AI, we want it now. That's the trouble. We want it now. And the way to do it is to do knowledge engineering. I think that's the wrong way to do it. Totally wrong way to do it. We've got to do AI that's built in knowledge free. It'll be much slower, but it'll be much more robust and capable in the environment it's going to be in. I face this dilemma every time we do research. How much to build in, how much to let it be knowledge free. Built-in knowledge free that is not building in any knowledge, has to be the right answer in the long run. If you could just be patient and build agents. The question is, do you have to wait for evolutionary time? We don't. Here's an example of Go in which from 1995 to 2020, we went from knowledge heavy built-in knowledge approaches to building now, and there's actually a new version that's coming up in which it's really just learning from scratch. No knowledge built in. And that's the best scope layer. And that story that I'm showing on this slide will be repeated over and over, is my prediction, in all kinds of AI problems. The question is, can we wait? Can we not do what's available now? Last slide and I'm done, promise. Well, one more summary slide. This is Mike's. This is for Mike. I've been thinking about one more of how do we avoid the evolutionary slowness, scale, to get to AI. And the only idea I can think of that's feasible is cloud AI, right? AI in the cloud. That is to have lots and lots and lots of federated or other agents learning everywhere and pooling their knowledge to the crowd. The question is, how does this distributed set of AIs, how do they get organized? Right? We have ways of doing this in societies. We have a feudal system, we have a capitalist system, we have other systems. How would we organize distributed AIs so that as cloud AI becomes a reality, those distributed agents can learn and share their knowledge and avoid, because that's what evolution could not do, right? Evolution doesn't allow me to download Brian's brain into my brain. That's probably a good thing. That's right. That's right. That's right. But we can do that with robots, right? We can share all their learning, all their software, all their knowledge. So, but how does this get organized? How does this happen properly and well? There's just tons of really interesting questions here. This is how, at least one hypothesis of how we'll beat the evolutionary scale otherwise needed to do built-in knowledge-free AI. Okay, so this is my last slide. I'm going to stop here. There's lots of interesting questions. I've just listed a few very, very high-level questions that drive my research. Thank you all so much for your patience.
Some time for some questions. Mike, you want to ask a question?
Somebody has to start, otherwise no one will ask it, which is fine. Yes, Gil.
Can you go back to the slide with the two curves, the built-in versus there?
Yes.
Where are we now? Sorry, where are we now?
Well, the interesting question, one of the interesting slides is this slide, right? This is the Go slide.
Yeah.
Now, of course, Go is not everything. Far from it. But this is an example where all the early effort was about building in knowledge into the Go game. And then over time, we've moved further and further away from that, closer and closer to not building in anything. And now I've gotten really, really good performance. Now, of course, it takes Google scale effort to do that, right? So that has to shrink. But I think this story, by the way, it's true in many games in particular. Backgammon, the same thing happened. So, can we translate from games to other things like real robots? And that's where my answer was this one. I think we need a market of robots, market of robot minds that share and accumulate knowledge. There are tons of really hard challenges in doing this. But I think in the end, this is where we'll have to go, or one of the ways we'll succeed. Yes, Jesse.
Okay, so where AI is really killing it is when simulation and reality are the same. So games and simulation,
Yes.
they're the same.
Yes.
And where AI is tripping is when the torque into the robot has nothing to do with how the joint moves, okay? So
Right.
how's that gap going to be closed? Is that an AI problem or is that something else?
Good. Again, I'll point to the answer that says, so I think two things. There are people here who know more than me on this, so please speak up if you like. My view on this is that simulations are getting better and better. They're not there to the point that you were just suggesting. But simulations, a lot of great thought is being put into making better simulations and closing the loop from real to simulations. So that technology is getting better. So that's hopeful, which means more problems might be simulatable than than are true today. So that's one thing. The other thing, I think, is the same answer, which I just gave, which is we'll have to have lots of robots that are acting in the world and collecting real data. Now, each robot might be slightly different. Every environment is different. How do we do transfer? How do we learn from one robot's experience and transfer to another robot? Those will become the challenges. But that will be a path towards trying to solve the problem that you're getting at. When that'll succeed, I won't know. I don't know. Radha.
Thank you. This is great. You gave examples from evolution. And one could argue otherwise, but one of the theories in evolutions of human race is that our main reward is survival of the gene, which eventually that got decomposed. So we have the instinct of conservation or instinct of, like other instincts that we have of maybe having friendships or being generous and so forth.
Yes.
And you mentioned, which I think it's a very nice direction that one of your students is taking now, of decomposing reward functions. So one question would be, which way should we go? So eventually one could think of maybe even for robots getting all the way to survival of the genes for robots. And conversely, going the other direction, what would be the right granularity of a reward function for which robots eventually could react to that, or in general, machines?
So, good. I think survival is an extremely strong instinct, of course, and but if the agent is doing well, that itself can't drive. It's too distal and too infrequent to really drive behavior, and so the optimal rewards problem tries to drive useful reward functions. So. So I think social rewards, because we are social animals, is a very big part of the intrinsic reward function space. So the bottom line for me is that I think the optimal rewards problem gives a framework. What I'd love to do with the optimal rewards framework is derive reward functions that are good or near optimal in classes of environments. And that way we might be able to discover what kinds of reward functions are useful for what kinds of environments. We haven't done that yet. But I think that's the research path that I'm wanting to head down, is being able to essentially build a catalog. For these kinds of environments, this kind of intrinsic drive or intrinsic motivation is useful. Or this distributions of over these environments, this kind of intrinsic motivation is useful. Haven't gotten there yet. But that's the goal.
Do you think the best learning agents will be ones that learn everything from a blank slate, or ones that have some knowledge inbuilt into them? Because evolution itself seems to have found a balance where even newborns seem to have some innate knowledge.
None of this was to argue that people are born tabula rasa. It's about how to build truly capable AI. And that's the question. The premise of this graph that I'm showing is that human built-in knowledge built-in by us, is going to be knowledge that's learned by the agent and represented, derived from the experience the agent has, will automatically be verifiable and maintainable. And that's the difference between usual built-in knowledge from humans versus learned knowledge. Having said that, we just talked about how to download brains from one robot to another robot, right? Software from one robot to another robot. So robots will not have to be tabula rasa. They can use knowledge learned from previous robots, just like evolution does in some sense. So there are ways we don't have to build robots from scratch. Thank you very much.